Okay, good. All right, thanks, Phil, for the introduction. I'm very glad to be here and honored to be invited to the Rogue World workshop. So as Will said, I was assigned this title. So I was tasked by the organizers to give an overview of some of the fundamentals of planet formation theory, which of course is a vast topic. So what I'm going to do is I'm going to focus on the early stages of planet formation in a general sense, and then towards the end, I will try to make some connections that is to something that's more germane to the main topic of this workshop, which is about the real world. And just a little advertisement. So I'm currently a faculty member at McGill, but I'll soon be joining a brand new Department of Astronomy and Astrophysics at UC San Diego. So keep that in mind if you have students or graduating or looking for jobs. All right, so I always like to start things off with some data. So this is the confirmed exoplanets and mass versus orbital semi-major axis, and we've already seen different versions of this plot yesterday. And the color coding is with respect to the different detection methods, and the contour lines are the sensitivity limits for these different techniques. And as was pointed out, and I think most of us know how there is a blank spot in the bottom right corner where there's no data, and that's not really physical. That's just because it's extremely difficult to detect these small planets at intermediate to wide orbital separations. And curiously, that's where most of the solar system planets lie. So at least for the next few years or so, you'll note that there is one contour line going through. It's labeled as microlensing space. That's basically Roman. And this really is, at least for the next few years or so, like one of the only techniques that will be able to probe the small rocky planets at these few AU or even larger orbital separations. And that is exciting, not just because we'll be able to finally fill up this spot, but also when it comes to planet formation, this is a cleaner probe of planet formation as compared to the data at shorter orbital periods where you do have to worry about post-formation processes that are further sculpting the planet population. So things like photoevaporation, tidal, and magnetic interaction between the stars and the planets. And furthermore, we are at the shallower ends of the gravitational potential well. So these are also the spots where you are more likely to produce rogue planets by dynamical ejection, again, under the premise that dynamical ejection is the primary mode of the formation of rogue planets. Just much easier to kick things out when you're farther from the central star. All right, so how exactly can we use this population to constrain or learn something about planet formation? And one way to do this is to do that one-to-one comparison between the data and the theory. And when it comes to things like microlensing, one of the fundamental observable is the mass function or mass ratio function if you do not have the properties of the stars readily available. And here's one example where that direct one-to-one comparison has been made. And you will note that there are a lot of different lines that correspond to the different models, doing a large parameter scan. And something to keep in mind that when it comes to the fidelity of these models, it hinges on our understanding of the protoplanetary disk, which gives us the initial condition of planet formation. And disk physics is really hard. It's really hard to know in detail the physical properties and the evolution of these disks. So that's where most of the uncertainties lie. So just to list a few, let's start with the very basic mass reservoir, the gas and dust. So starting with the gas, when it comes to gas disk evolution, one of the sort of a biggest uncertainty is how exactly the angular momentum gets redistributed over time. And that's often parameterized with some sort of unknown level of turbulent viscosity. We still don't know what exact microphysics gives rise to some level of turbulence that allows for the evolution of the gas disk. So we parameterize it with some kinematic viscosity as written here, or very often discussed in the community as the Shakura-Snayev turbulent alpha parameter, which is a non-dimensional parameter that gives the strength of the turbulence. And that's really hard to directly measure because turbulence within protoplanetary disk is highly subsonic rather than supersonic. Now, what about the solids? So in general, we know that the solids undergo inward radial drift, and there are some observational evidence for this in the disk community. So why does it undergo radial drift? That's because the gas moves more slowly than the dust, because it is moving at a sub-Keplerian velocity, at least in a smooth disk, due to the negative pressure gradient force that acts in the opposite direction to the stellar gravity. So the slower moving gas will drag on the solids, and the solids will lose its angular momentum and therefore undergo an inward radial drift. However, this degree of radial drift depends on some unknown Stokes number, or the degree of coupling between the solids and the gas, which is defined as the aerodynamic stopping time. That's how long it takes for the grains to reach its terminal velocity in the units of local orbital time. And this one is almost impossible to directly measure because you got to know the physical size of the grains, which you can only probe like with the multi-wavelength observations. And also you got to know the volumetric density of the gas as well, which is really uncertain due to the optical depth problem. And this exact same aerodynamic drag and therefore Stokes number, this will also determine how rapidly the planetary sized objects will grow in mass. And we're going to discuss this in a bit more detail. And also, once the planet forms to a certain mass and it's massive enough to perturb the surrounding gas disk, and those perturbed gas will torque back on the planet, and the planet is expected to undergo an inward radial migration. So typical type 1 migration that people talk about in the community. However, both the magnitude and the direction of the migration depends on the disk properties, including this turbulent viscosity that I have mentioned. So if your disk happens to have a low viscosity, and when I say low, I'm talking about the alpha parameter that's on the order of few times 10 to -4, which is actually not that crazy, then the planet would actually prematurely halt this migration. And that's because when you have that perturbed gas, and there's not enough viscosity or the level of diffusion, then as the planet moves in, the gas downstream to the planet's motion will just continue to pile up and pile up and pile up because there's just, it doesn't have enough time to react to it and try to diffuse that away. So the inward torque will just balance the outer torque, and eventually the net torque will go to 0 and the planet just stops its migration. So what does this mean? It means that these two fundamental parameters, this turbulent alpha and the Stokes number, it pretty much determines all the early stages of planet formation, where exactly the planet would form, how rapidly it would grow in mass, and where it would end up once it has formed. It basically determines where exactly we would see these planets in that mass versus orbital semi-major axis diagram. Yet, as I mentioned, these parameters are extremely hard or impossible to directly measure. So what can we do about it? And of course, one way to do it is to do a large parameter scan, but another way to think about it is try to see whether we can independently constrain these two parameters. And one way to do that is to make use of the ringed disks. So in the past few years, one of the biggest lessons we've learned from the disk community is that, at least for the nearby bright disks, many of them show this ring-like substructures. And these are considered as some sort of like a local concentration of dust due to some sort of a pressure, gas pressure perturbation within the gas disk. That acts as a trap of the dust. And the reason why there's a trap is because if, let's say this is a pressure trap, the dust grains coming in, due to the exact same aerodynamic drag that I have discussed, the dust will go in, but then it cannot go too far inward because on this side, the pressure gradient force now is acting in the direction of the stellar gravity. So the gas is moving more rapidly than the grains. So now the grains are going to gain angular momentum and move outward. So the aerodynamic drag causes a collection of the dust within the pressure bump, but that collection cannot go to infinity and create like a delta function because there's always some sort of like turbulent diffusion that's going on. The fact that we see these rings over a few million year timescales, the typical ages of the systems, tells us that there is a steady state balance between these two forces. And based on that steady state balance, we can write down the width of this dust ring in terms of the width of the gas pressure bump, which is on the order of the gas disk scale height, corrected for the relative strength between diffusion and the drag. This one we can directly measure from the thermal emission profile. This one we can estimate using the irradiation heating from the star. So we can now get this ratio between the Stokes and alpha. But that is not enough because we need to separate out the Stokes and alpha. So we need another equation that relates the two. So how do we break that degeneracy? Well, we go back to this radial intensity profile and take a look at integrated continuum flux, which will give us a probe of the total ring dust mass. And then we connect it back in time to the primordial mass reservoir of the disks from the class 01 disk. This is not Titori disk, this has to be class 01 disk. And we connect this back in time by integrating back in time the radial equation of motion of the dust grains. That includes the coupling to the gas radial motion, which includes the turbulent alpha, and the aerodynamic drag, which includes the Stokes number. So simply put, all we're doing is we're going to solve for the degree of the radial motion of the grains so that we can explain the total ring dust mass at the age of a given system. So that will give us another equation that relates alpha and Stokes. We have two equations, two unknowns. We can now solve for Stokes and alpha separately. And here's the result for the nearby well-resolved rings and ring disks. The upshot is the Stokes number is rather low and the alpha is also rather low. This is actually low enough that once the planets have formed, minimal level of migration is expected. They will prematurely halt, at least in the region where we see these rings. Well, let's track back a bit because we've talked about that when the planets form, they will undergo minimal migration, but can we actually form the planets in these rings? So it's a bit difficult because if you want to start with, if you want to start with the creation of the planetary seeds, even the seed creation is a bit difficult. And that's because for this level of turbulence, although it is rather low, the Stokes number is also low. So particles are just way too well coupled to the gas. It's really hard to peel them off from the gas flow and collect them and let them clump. But there are different ways in which the dust can clump. So let's say you were able to form the planetary seeds. And then let's ask the question of, can we grow them into planetary size objects? And when I say planetary size, I'm talking about at least like a Mars mass. And the answer is no if you're beyond the 10 AU. But the story changes when you go inside 10 AU. When you go inside 10 AU, then even for the small Stokes and alpha, the dynamical timescales are now short enough that you can allow for very rapid pore growth and have at least like a Mars-sized objects. This is interesting because this is consistent with the gas giant demographic survey from the direct imaging and the radial velocity surveys, where we see that there is a drop-off in the number of gas giants beyond 10 AU as compared to inside 10 AU. But in the theoretical analysis we've just seen, the planet that we're forming is not really, it's not even Jupiter. We're trying to form like a Mars-sized object, and even that was difficult beyond 10 AU. So what that might suggest is that we might see some sort of like a global fall-off even for the small planets. And this can be readily tested when we go for and measure the mass function, but now that versus orbital distances, and see whether we see some sort of like a global decline inside versus outside 10 AU across a wide spectrum of the planetary masses. All right. Okay, so let's now look into the region where we can actually form planets. So let's focus our attention to inside 10 AU. So think like 1 to 10 AU. And let's now think about what is the expected shape of the mass function. And before I do that, I'd like to give a little primer on pebble accretion, which is what we expect to happen in the early stages of the planetary growth. So the picture is that you already have some massive clump and there are grains zooming by. The classical picture is that you can define the effective accretion cross-sectional radius by taking the geometric radius and correcting for the gravitational focusing factor, which compares the relative energetics of the incoming particle with respect to the gravitational potential of the clump. Now, obviously, it's going to be easier to accrete the particles that are less energetic. And this is where, at least at a heuristical level, Hubble accretion can come in handy. Because the idea is that there's always the gas drag, and not only does it remove and sap away angular momentum, it can also sap away momentum. So the grains will, the energetics of the grains will easily decay away until it can easily settle and spiral onto the gravitating object, effectively increasing the accretion radius. Now, the physics here is aerodynamic drag, and recall that aerodynamic drag is controlled by the Stokes number. So the efficacy of this accretion is very sensitive to the Stokes number, and in fact, it is not monotonic. If you're dealing with Stokes number that is too small, then the dust is just so well coupled to the gas, and it's really hard to peel it off the gas flow and let it settle onto the clump. So the accretion rate is going to drop. And you also do not want large Stokes number because at that point, the inertia of the grains are just too large, and they're just not going to care too much about the aerodynamic drag. So this pebble accretion is maximized, the accretion rate is maximized for the particles that are marginally coupled to the gas. In other words, Stokes number of on the order unity. But the exact same aerodynamic drag also causes the inward radial drift. So we can define the efficiency at which we can form this planet by taking the ratio of the accretion rate to the radial drift. In other words, what is the fraction of the drifted material that you can accrete onto this planetary scenes? And if you do the actual calculation, it is a pretty small number, especially at the wide-ish orbital separations that we're interested in. The efficiency is going to be on the order of 10% or lower. And this is important because we can use this to construct the expected primordial planet mass function. And we're going to define that by using what is the fraction of stars that is expected to primordially form the planet mass at a target mass bin, which you can calculate as a planet formation efficiency that we just discussed times the disk mass function. This is the disk mass function, and again, this has to be class 01 disk because T-Tori disks are already processed. And we have to go back to the primordial mass. So this is a very initial mass function, and we're actually focusing on M-dwarf objects, so the stars that are expected to be the most abundant. And if you take that analysis, generally speaking, your primordial planet mass function is going to look rather bottom heavy. So just to decode this a bit because there's way too much going on, you'll note that the degree of the bottom heaviness depends on how M naught is the initial seed mass. So if you start with the seeds that are quite large, then you don't need as much extra mass within the disk to grow that seed to sort of like the animated moon-sized object, sort of like the smallest mass bin that you would be most sensitive to. As compared to when you start with the initial seeds that are quite small, then you need a lot more extra mass within the disk to grow that seed to the Ganymede-sized object. So that's why it gets more muted, depending on what kind of initial seed mass you're dealing with. So observationally speaking, if you, depending on the slope of the mass function, you may be able to say something about the very initial sort of typical seed masses of planet formation. However, this is primordial mass function, and what we are observing is not primordial. So the picture here is that you have a whole bunch of small mass objects within a given system, and if you just let them go over a few hundred million year time scale, they're going to undergo dynamical interaction. So I'm going to go through this very quickly, not just because of time, but also because this is going to be expanded a lot more throughout today's session. Very heuristically and very generally, the lower the mass of the individual objects within a system, the more softer the close encounters are going to be. So at best, you might see like a merger events. And the larger the masses of the bodies, the more dynamic and dynamically hotter the interactions are going to be. So you might see a lot more ejection. So if you actually take these systems and let them undergo n-body integration, then what we see is that there's a bit of a divide right at around third of an Earth mass. Below that, we see a lot more stability. Above that, you see a lot more mergers and ejections. So at least at face value, this means that you might expect a bottom heavy and probably bimodal bound planet mass function at around like an Earth mass or so. And actually a top heavy free floating planet mass function, because that's more likely to occur at an Earth mass and larger. But as we have discussed yesterday, at least for the current ground-based microlensing surveys, we might be seeing the opposite, although I think the jury's still out there because of it's just really hard to probe down to the very low mass objects. But let's say you go, the Roman goes up and you recalculate this and you still see the rogue world population to be a lot more bottom heavy than the bound planet population. Then that actually says something interesting about what is the criteria for the planet formation when it comes to disk properties. And they have to be massive enough so that they can at least primordially create Earth and super Earth type objects, as well as the smaller counterparts. All right, so to summarize, we started our discussion with the mass versus orbital semi-major axis, pointing out just how special this population of planets would be. And in terms of theoretically predicting what we would see and what we might see, we really got to understand better the disk properties. And in particular, there are two fundamental parameters that control pretty much all of the early stages of planet formation. That is the Stokes number and turbulent alpha. Using the ring disks, we find that they are small enough that once the planets form, we would see minimal level of migration. But the planet formation itself is going to be difficult outside 10 AU as compared to inside 10 AU, which again can be readily tested by looking at planet mass function, but as a function of different orbital distances. And then if we focus our attention inside 10 AU, so the region where we expect to see a much more vigorous planet formation, then what we just naively expect is a bottom heavy and bimodal bound planet mass function at across like one Earth mass or so, and perhaps more top heavy free floating planet mass function. And if that's not borne out in the data, then what that means is the planet population that we see, both bound and unbound, has to come from disks that are massive enough that they were able to create at least Earth to super Earth size object. And that actually, I think, says something interesting about the galactic census and comparison with the overall disk mass function, because that is not the majority of the disks that we currently see. Thank you.
So much. Okay, question time. So yeah, Dave.
So you have that line drawn at 10 AU, but can you tell us how that depends on the host star mass?
Yeah. So it's mostly based on the dynamical time, and dynamical time goes as square root of the stellar mass. So it's not going to be it's not going to be too sensitive to the stellar mass.
Okay. There are questions for you? Yeah.
Thank you for I want to ask about the occurrence rate in the product, more than 10 days. So the minimum migration is to the lower occurrence rate in larger major axis. You said how about the scatter something like wide orbit, high eccentricity planets case?
So are you asking how do we explain the wide orbit planets in this picture?
Yeah, so that it is possible to detect the migrating the scattered planets.
Yeah, so right. So to clarify, this picture is purely just like primordial formation within the disk. But like if you have like very high eccentricity wide orbit planet, that's probably like scattered by dynamical interaction. So that will be sort of a next step after after the formation. But like if they all have to happen beyond 10 AU, which actually sort of like scattering can start like from 1 AU too. So like all the scattering might actually initially happen in a region like between 1 and 10. Although it is, yes, it is easier like once you're much more beyond. That wouldn't like necessarily say that you would expect a much more like reduced population.
Other questions? Yeah.
Can you tell us more about this dynamical figure where you show that the larger the orbital distance is, it's more likely to get ejected? Is this based on the assumption that they're all like equal mass and there is no, let's say, another dominant scatterer like nearby?
Yeah.
So it's like similar size planetesimal or protoplanets scattering each other.
Yeah, so this picture, the simple picture that I showed, so this one is simply just an energetic argument. So this is just saying, okay, like what is the maximum energy that I can impart by some object where the object is mass on the y-axis. So that's just the surface gravity divided by the bounded temporary velocity. So like is there enough surface gravity to kick these out at that location? That's all that plot is. In terms of the picture that I showed of like how you might expect this, so that comes from where a given system has not actually equal, but like similar mass objects. So that's why I mentioned that like if this is not borne out in the data, then what you need is a mixed system where you have at least super Earth and Earth, like a bit more massive objects, as well as the smaller mass counterparts, so they can kick them out by the larger mass. It does not take into account like let's say stellar binary. That's like another perturbation, adding another perturbation to the system.
It's for the congregation.
Any other questions? If not, I had a quick question for you. So, so first of all, the takeaway here is that you say you expect a top heavy FFP mass function, correct? So roughly where would you expect it to fall off? Like, you had this sort of
Earth mass.
An Earth mass. So below an Earth mass, you expect it to be significantly fewer.
Yeah, if the picture is that like you started with like similarly mass objects within a given system.
Okay.
Yeah, so to this primordial mass function. So this primordial mass function, especially like this thing, what this corresponds to is that this is the fraction of the stars with the disk where you don't have enough mass to create the larger objects. And this part would be stable, so they will not be kicked out because you just have like a whole bunch of like smaller objects. And all that kicking out will just be dominated by the Earth mass and larger objects. So that's where this statement comes from. So like if you see the opposite, then that means the planetary population that we see must be dominated by the more massive disks within a larger population.
Okay, really neat. Thank you so much.